This is a pre-GA demo of Session Smart Routing for classified, specifically the ESP-based version. And so what SSRFC is a double bookended SVR-based network architecture where we have our black network in the middle running SVR, our type 1 encryption providing IPsec-based transport between the two encryptors or the CFFC stacks, and then our enclaves, so in this case a red enclave. And what we're able to provide is seamless integration with the existing solutions that are out there, so either HAPI Type 1 or CFFC. Zero additional overhead, so zero overhead even for L2 VPN. So SVR is a encapsulation-free mechanism, so there's no tunnels, there's no overhead of tunnels. And then we also can apply, multi-layered encryption, a lot of entropy in the network, and we can also provide diversity of paths. We're transport agnostic, so I don't care exactly what type of transport it is, just that it is IP. We also provide a mission-aware session routing in QoS, and I'll go into a little bit about what that means. And then everything works completely disconnected, so full DDoS operations as well as edge situational awareness. So you can see from the red side the state of black side transport, and everything's 100% software. So core to what we're doing is basically routing sessions and using SVR to operate in an environment where typically it's very, very difficult. And so what happens is a user is going to initiate a session. That session enters the SSR. We then map tenant and service. And then we apply service policy to that session, which will control numerous different things, one of those being marking of that traffic. And so the traffic will then be marked as it egresses the router towards the type 1 encryptor. Those markings will then be reflected. And then what's happening on the black side is we've set up policy specifically looking for the combination of these specific mappings. So we're looking at the source tenant, the destination HAPI, and then the specific DSCP marking to define the specific service, which then influences everything about how that traffic is going to be treated. And you can create up to 63 different services per SA. And then that session is then controlled with that session specific policy on the black side using that DSCP mapped service. And then when you have non-mission activity, that's going to enter the SSR. And then from there, we can then map that traffic as well. So in practice, what you'll see is a red side router, mission, non-mission activity going in, that traffic then being marked, the markings being reflected. And then on the black side, we're going to use the context of the source of that traffic. So in this case, that specific red encryptor, its destination, and then the marking to identify the service. That will then influence how we're going to route the traffic. And then we can also strip those markings out before that traffic is transmitted because we're not reliant on the markings for this to work. And we can also apply different encryption keys per session and path. And then when the traffic gets to the other side, we can then reapply those markings and then send that traffic on to its ultimate destination. Further, when it comes to actually the key exchange, IPsec's a two-phase operation. So there's the first phase, which we're exchanging keys. This happens also during the rekey interval. And then you're sending the data in ESP. And so we actually can enhance the security of that process by doing a protected key exchange. So to ensure that IKE v1 only traverses trusted paths, we could do assured key exchange to utilize packet duplication to send that traffic across multiple different transports at the same time to make sure that that key exchange event is successful in lossy environments. And then you can also set a preferred key exchange. So I want to prefer specific trusted paths, but also allow others in the event those aren't available. Some of the key capabilities that we provide are well beyond zero trust. And so those are around stateful QoS, session routing, message assurance, and then encryption. So for stateful QoS, on the session side, we're able to control the bandwidth and overall burst of an individual session. And then this is a global setting that you can apply across every single router. You can control it on the service level. So controlling upload, download per service or for a group of services. These rates are locally significant to the router. And this controls overall and burst as well. Interface-based QoS limits. So there's an outbound queue on the interface. You can apply this. We have a high, medium, low, best effort queue per device interface. And then that queuing can be done on any interface, so WAN or LAN side. Per peer, so we'll actually define the capacity that a router is able to consume, and then we'll tell far side routers of that capacity to avoid them being overwhelmed. And you also allow to differentiate upload and download rates. On the session routing, we define path options using vectors. And so we can set orders and weights to determine which specific paths we're going to take. And also the ability to exclude vectors to make sure that you don't go over certain paths that you may not want to. When it comes to picking paths, you can use vector priority, lowest latency, highest MOS score. When it comes to load balancing or SLA enforcement is going to be used to exclude paths based upon an SLA violation. And that SLA is derived from BFD or passive in-session performance monitoring. When it comes to load balancing, we're going to take that SLA into account, and then we'll use things like hunt to prefer the most optimal path over others, proportional to distribute sessions across different paths based upon weights, and then capacity. So we actually can look, is the interface over capacity? And if it is, we'll wait till we hit a low watermark before we add new sessions onto that path. On a failover side, we can choose not to failover. We can choose to failover to the next best available path, or we can choose to failover and then fail back to the most desirable path if that desired path either comes back up or it begins to meet the SLA again. When it comes to message assurance, we can do things like packet duplication, where we'll send packets for a specific session across multiple paths, so essentially all available paths, to ensure the delivery of those packets. We have adaptive FEC in 5.5, which will detect lossy paths and perform adaptive forward error correction to decrease the probability of packet loss between peers. This is a separate function of packet duplication. They can be used in conjunction. And there's also non-critical backoff, where we can stop or limit non-critical traffic based upon a path SLA violation. And so, for example, if you start to incur lots of latency or loss because of jamming, we'll actually be able to identify that's occurring and then stop additional traffic from traversing the WAN. On the encryption side, you can set security policy for a specific service, and this can be applied to a single or multiple services. And what this does is it defines the keys and algorithms in use. It defines the default encryption state, either disabled, enabled, or adaptive. And with adaptive, we can automatically detect whether or not traffic is already encrypted. So we'll look for TLS or ESP. And then this provides a way of enhancing cryptographic entropy by using multiple different security policies. So a single IPsec session can then be split across multiple different services with different security policies, different encryption keys used for each. And there's also peer and path-based encryption. So what this does is, if you say, I never want to encrypt, but only if we traverse these specific paths, I want to add encryption. And so, for example, I only want to encrypt when I'm going across commercial transports. So let's dive into a interactive demo. I'm going to go through the environment that I'm actually going through myself. And so we'll see kind of what that looks like. So in my demo environment, I have a couple different things set up. So I have my black side routers, in this case, 2 SSRs, and we have 2 simulated transports, an LTE and a microwave. I then have my SRX, and in this case, this is simulating the type 1 encryptor or a CFFC stack. And then I have my red routers. And so I've disabled orchestration just to kind of save on some resources in my lab. And what I'm going to do is go ahead and kind of show you what we can see. And so if we take a look here, this is the red side router. And what I can look at is the current latency that's going through the network. I can see the sessions because all this stuff is in the clear. And then I can see how much bandwidth is being consumed by different services. And so what's nice is that if I go into my topology and I inject some latency into the network, let's say we inject 100 milliseconds of latency. What I'm going to see is the latency on that LTE path is going to go up, because that's the one that I've modified. And we can see the latency's just jumped up. And so I'm able to perceive on the red side what black side transport is doing. So we can look at latency loss, jitter, all that stuff is visible from the red side. And then in addition, I can then make decisions about that traffic. So what's happening on the black side is we're routing a specific service in different ways. And all that traffic that's coming into the router, if we take a look at the actual PCAP, what we can see is it's all ESP traffic. The only thing that differentiates it is the markings that are applied to that traffic. And so the way that we differentiate those markings is with the DSCP steering technology that we've just released. And so in this case, we create a core, a parent service, in this case called SSR, and then we create different mappings for those different DSCP values. So in this case, a value of 1 is going to have a treatment to go over the LTE. And in this case, it's going to go over LTE and there's no failover that's applied. If, for example, the service was a DSCP value of 25, this has a service policy called prefer MPLS. And this one's going to prefer MPLS or LTE, and it's set to do revertible failover. So we can take a look at here is this is the different breakdown of individual sessions from that specific IPsec tunnel. And then if I go and, for example, run a speed test, this is going to go over my LTE connection, which has over 100 milliseconds of latency. I can see the bandwidth that's being consumed. And then we can see the fact that right now it's going across LTE. It's actually given a DSCP value of 1. And then if I were to go and say, for example, download an ISO file, this is going to have a different treatment. So we can see all of our service for speed test is here. And then in a second, we'll see our traffic that's going out, in this case, to download that ISO file. And there it is right there. So that's the download of an ISO file. And so this has, a different service, which then gets a different service policy, which then gets different marking, which then is reflected, which then when we get to the black side, we can see that that traffic is now showing up with a value of 25, and it is traversing the microwave path, right? So we've gone from being on the LTE path to the microwave path just by changing service policy that's on the red side of the network. So we're able to get full visibility with no additional overhead and the ability to control the traffic very, very easily, as well as do failover. So right now I'm downloading that traffic. If I go ahead into my path right here and I suspend that link, what we'll see is the traffic will basically just keep on going, because that's exactly what it's going to do. So we did failure in less than a second, and we've transitioned from one path type to the other as a result. And over here, everything just keeps on rolling. So this is a very short demo of what we're able to do with SSRFC and kind of the architecture that we're using in these very sensitive environments. Thanks for watching.